Electric field and capacitor structure question assignment. Yesterday we did the first 6 questions from this assignment, and today we'll do question 7 onward. You will find similar questions, like a pattern is there when you're solving the question from this. Question 7. A timer circuit included a capacitor and a variable resistor in series. So there is a capacitor and a variable resistor, both are connected in series. The graph shows how the current in the timer circuit vary with when the capacitor discharge. So this is discharging. The current is shown through a variable resistor, which is having a resistance of 8.2 kilo ohm, or we can also say 8,000, 200 ohms. Show that the capacitance of a capacitor is about 0.2 microfarad. So we want to show that the capacitor which is used here for this, for discharging, its capacitance is about 0.2 microfarad. So what we can use, because the graph is there with the current, so we can use a formula that I is equals to I naught e raised to power minus t over RC. And whenever you're using a graph, you should show your working. You should draw the lines, the points which you are taking on the graph. So what is the maximum current in this? The highest current, which is I naught here. So using the graph, each box from 0 to 10, like the 10 boxes equals to 0.5. So each box is 0.05. So this is, this will be 2.1. This will be 2.2. This will be 2.3, and looks like 2. Like it matches about here, so it is 2.4. So the maximum current, the I naught is 2.4 milli. So you have to convert into ampere. So you divide by 1000, or you can say 2.4 into 10 power minus 3 ampere. Then what about I? You can take any of them as I. It's up to you, because then you need a specific time interval. Example, I'm taking this 1 ampere as I. So this will be I. It means it is equals to 1 into 10 power minus 3 ampere. And what about the time interval? So it started with 0. And then when the current is 1 ampere, this will be the time interval. So each box, 10 boxes equals to 50. Each box is 5. So it is 105, 10, 15. So 115 is there. That is in second. Now we'll use a formula that I equals I naught e raised to power minus t over RC. So the current I is a current at a specific time interval, which is 1 milliampere. I naught is a maximum current, is beginning 2.4 into 10 power minus 3 ampere. E raised to power minus t is a time to change from I naught to I, that is 115 seconds. R is the resistance through which the capacitor discharge, that is 8.2 kilo ohm, so 8.2 to 10 power 3, and multiplied by capacitance C. This 2.4 exponent minus 3 is multiplied with the other side, it will be divided. So it will be 1 into 10 power minus 3 divided by 2.4 into 10 power minus 3. And then e raised to power minus 115 divided by 8.2 into 10 power 3, and then C. Then what we do, we'll take ln both sides. So when we take ln both sides, so it will be ln of this number by 1 into 10 power minus 3 divided by 2.4 into 10 power minus 3. That is ln. And then ln cancelled with these, so it will be minus 115 divided by 8.2 into 10 power 3, and then C. Then we simplify and get the capacitance of this capacitor, which is about 1.6 into 10 to the power minus 2 or 0.016 will be there. When we simplify this capacitance, it will be 0.016 farad. The unit of the capacitance is farad. Is it clear, this part, that how we worked out the capacitance of the capacitor used for this circuit? The next, calculate the initial charge on the capacitor. So what was the initial charge the moment when the capacitor discharged? So what is the initial charge? So first, the initial current, first we'll find the initial voltage, because we should know to get the charge we have the formula Q is equals to CV. We already worked out the capacitance in the previous part, which is 0.016. But what about the voltage? So how to work out the voltage, initial voltage across the capacitor? So V is equals to IR. Where I is the initial current and R is the resistance through which the capacitor is discharging. So initial current was 2.4 into 10 to the power minus 3 because it was in milliampere. And the resistance through which the capacitor is discharging is 8,200. So when we multiply them, the initial voltage across the capacitor is 19.7. So 19.7 is the voltage across the capacitor, and its capacitance from the previous part is 0.016. So the total initial charge is equals to 0.316 coulombs. That's the initial charge which is stored in the capacitor. Then calculate the initial energy stored in the capacitor. So how much energy stored? So that is given by a formula. Energy stored is equals to half the total charge into total voltage, like initial charge. So the maximum charge which is there, this capacitor 0.316, and the voltage across the capacitor is 19.7. So the energy, the total energy which was stored in the capacitor is 3.08 joules. But we cannot say that the capacitor is stored charge. We always say it's stored electrical energy. In part B, in another timer circuit, the capacitance of a capacitor is 470 microfarad, means 10 to the power minus 6. The circuit switch off when the potential falls to 15% of the initial value. The variable resistor is adjusted so that the timer circuit switch off after 3.5 minutes. Calculate the resistance of a variable resistor. So the capacitor circuit switch off when it reaches point 15% of its original value. So we'll use the formula V is equals to V naught e raised to power minus T over RC. So 3.5 minutes we have to convert into seconds, so we'll multiply it by 60. Like it started with a maximum voltage V naught and it switched off, as I mentioned, when the potential difference fall to 15%. It's not like, so it means this is a value which is there, like it will stop working. So V is equals to 15% of V naught, like it was working, that is the start and this will be the stop. So 15% of the V naught, it stopped. So 15% means 0.15. So we can say 0.15 V naught is equals to V naught e raised to power minus T, which is 3.5 into 60, because we have to convert into second, divided by R is the resistance and C is the capacitance, which is 470 micro farad. Micro means 10 to the power minus 6. V naught will cancel with V naught. We'll take ln both sides. So ln, so shift ln 0.15 is equals to, when we take ln here, it will cancel with E. So we are left with 3.5 into 60 divided by R into 470 into 10 to the power minus 6. So we need R here, we cross multiply. So R will be equal to minus 3.5 into 60 divided by ln 0.15, and that is multiplied by 470 10 power minus 6. So after simplifying, we get the resistance, which is about 2.3 exponent 5 ohm. So 2.3 into 10 power 5 ohm will be the resistance. In question 8, the diagram shows the path of an electron deflection tube. How it works? Because electrons, as we discussed in AS, that we can produce electrons by two ways. One is a photoelectric effect, another one is a thermionic emission. Thermionic emission means by supplying the heat energy to a metal, like electrons are there within the metal, inside the metal, we supply the heat energy, electron gain energy and go out. That is called thermionic emission. Therm means heat and ionic here refers to that electrons or charges are moving. And another one we discussed, the photoelectric effect, which shows the particle nature of the light. So the photon absorbed, like if the energy of the photon is equals to the work function, which is a minimum possible energy to remove electron, this electron will go out. So normally in a electron gun, we use the thermionic emission. The electron gun consists of a hot metal filament and a positively charged anode. Why this produce a beam of electron? What is the reason why a beam? As you can see here, this is a positive charge electrode is there, and it is having a hot metal filament. So what is the advantage? So electrons, because when the metal become hot, the electron gain energy and it comes out due to thermionic emission. And what is the advantage of having anode? So electrons are accelerated by the electric field, or electron can be moved by the electric field of anode. So why the hot metal is there? So it can produce electrons by thermionic emission, by heat. And why there is a charge anode, positively charged anode, that is used to accelerate the speed of the electron. So accelerate the electrons. The potential difference between the hot metal plate and the anode is 2.1 kilovolt. Calculate the velocity of the electron as they leave the electron gun. So here what happened, the electrical energy changes to kinetic energy. So idea is that when we supply, like we apply the voltage, so we are providing electrical energy. So the electrical energy will be equal to kinetic energy. Kinetic energy is given by a formula half mv square, and electrical energy is from the supply is voltage into charge. So we need the speed. 2 will be multiplied and m will be divided. So v square is equal, this v is the speed, this v is the voltage. So voltage into charge multiplied by 2 divided by mass, and then take a root. So v is equals to under root VQ into 2 divided by M. So the voltage which we applied, that is 2.1. So 2.1 kilovolts, so 2.1 into 10 power 3. Multiplied by charge, because we are accelerating electron, so we'll take a charge of 1 electron, which is 1.6 into 10 power minus 90. Then it is multiplied by 2 and then divided by the mass. What is the, because we are accelerating the electron, so mass of electron is 9.11 into 10 power minus 31. And for this, we'll take a root. This will give us the speed at which this electron is emitted out, which is about 2.7 exponent 7 meter per second. So whenever we use electric field to accelerate the particle, the electrical energy changes to kinetic energy. The electron beam passes between the plate across the potential is applied. The electron beam is deflected up. So if electron beam is deflected up means the electrons are positive, electrons are negative, so they are attracted toward the positive plate. So which plate is positive? Top or bottom? So which of the plate is positive plate? As the electrons are going up. So top is the positive plate and the bottom is the negative plate. So here it means this will be the positive plate. We don't have to write a chart, but because we have to draw electric field. So electric field lines, remember, from positive to negative. So, and when you draw the lines, it should, because between the two parallel plates, the electric field is constant. And how we represent? So we should draw the lines equally spaced. If in exam you draw like some parts, you draw more lines, some parts you draw few lines, then it means it is not non-uniform. So that will be considered as wrong. So whenever you draw them equally spaced, and near the curve, near the edges, it will be curved, as it's a non-uniform. In part D, the potential difference of 550 volt is applied across the plate. The vertical separation is 5 centimeters. Show that the electrostatic force on electron is about 2 exponent minus 15 Newton. So what happened? This electron, like first, the idea is that when we produce the electrons, these electrons are able to pass through in a straight line. But when we apply the electric field, one top side positive, bottom negative, so we observe a deflection, that electrons are deflected or deviated or changes the path. The vertical separation, or the vertical, like the how much it displays from the original position, that is 5 centimeters. The vertical separation of the plate is 5 centimeters. So this separation is about 5 centimeters. And the voltage between the plates, the two plates, the voltage is 550 volts. So we want to show that the electrostatic force between the plate is about 2 exponent minus 15 of the Newton. So we have the formula V is equals to ED. So electric field strength will be equal to voltage divided by. So electric field strength will be equal to voltage divided by distance between. So when V is the voltage between the plates and D is the spacing. And after that, because we need the force, so E is equals to F over Q. So F is equals to E into Q. So after getting the strength of electric field and charge, what charge we'll use, because we are accelerating an electron, so charge of one electron is 1.6 exponent minus 19. So first we'll find the voltage, first we find the strength of electric field between the plates. That is 550 divided by, this is 5 centimeters, so don't forget to convert into meter. So it is 5 into 10 power minus 2 because we divide by 100. So this will be the strength of the electric field, which is about 11,000 volts per meter, or you can also say Newton per coulomb. Now after getting that, we need the force. So strength of the electric field is 11,000 and charge of one electron is 1.6 into 10 power minus 90. So when we multiply them, we'll get the force, which is 1.77 into 10 power minus 15 Newton, which is about like 1.77 minus 15 is about 2 exponent minus 15. Is it clear, this part D1, that what is the force experienced by the electron when it is moving between the plates? Okay. Then the next, the electron in the beam enter the region between the plate with a horizontal velocity of 2.2 exponent 7. Determine the vertical deflection of the beam after it traveled 10 centimeter horizontally between the plates. So, like the two plates are there, the electron enter with a speed of 2.2 into 10 power 7 meter per second. This is the speed at which this electron enter the electric field. Then what happened? It will start to deviate, so it have two components. The horizontal component of the velocity does not change. Like the horizontal component, all the points, it will remain as 2. The horizontal component or at all the point remain as 2.2 exponent 7. But the vertical component will change. Like initial vertical was 0. Like when it entered the field, there is no vertical component. But because there is a force and the direction of the force on negative charge is opposite to the direction of electric field, so there's a force upward that cause a vertical acceleration or vertical change in the speed. So we want to determine this distance. We want to determine like from the center position, if it cover horizontally 10 centimeter, if it cover 10 centimeter between the plates horizontally, how much is the vertical distance? So first, using the speed and the distance, because we know the horizontal distance, we know the horizontal speed. So we'll determine the time it will take to cover this 10 centimeter. And using that 10 centimeter, then we'll determine this displacement. So we have the formula, speed is distance divided by time. As horizontal motion, there is no acceleration, so we can use this formula. So time is equal to distance divided by speed. The distance which it cover, that is equals to 10 centimeter. So it will be 10 into 10 to the power minus 2, which is 0.1, and divided by speed at which it entered 2.2 to 10 to the power 7. So when we divide, it will be 4.5 into 10 to the power minus 9 seconds. So that is nanoseconds. So it will take 4.5 nanoseconds to cover 10 centimeter. And it is obvious because the speed is so high, which is 2.2 exponent 7. So it will take a very short time to cross this distance. Now, we already have the force in the previous part. So using that force, we can determine its acceleration. So the acceleration in this, like the change in the velocity in this vertical plane will be force divided F is equals to ma, or A is equals to F divided by M. F is the force which it experienced, that is 1.76 into 10 to the power minus 15 divided by the mass of electron, which is 9.11 into 10 to the power minus 31. When we divide them, this will give us the acceleration, which is 1.9 into 10 to the power 15 meter per second square. Now, after getting the expression, we'll use the equation of the motion, because it is, so here initial vertical velocity is 0. We want to get this displacement. So we'll use the formula S is equals to ut plus half at square. Because initial velocity is 0, so S is equals to half at square. Or we can say S is equals to half. A is the acceleration. What about the acceleration of this? Which is 1.9 into 10 to the power 15. And T is the time it will take, which is 4.5 into 10 to the power minus 9. And then it will be square. So when we simplify this, it will be 0.02 meters. So the vertical displacement is equals to 0.02 meter. So how we solve this question? First, we determine a time. As I mentioned, like between the plate, it was there 10 centimeter. So if it cover a horizontal distance of 10 centimeters, so how much time it will take? We will use that time to know what the time to cover the vertical displacement. But to get the vertical displacement, we should know the acceleration, or we should find the acceleration, which is the force, and practically, like here, it should be a resultant force, but like electric force is upward and weight of the electron is acting downward. But we did not consider the weight of electron because it's having a negligible mass, like 9.11 exponent minus 31 into 9.8, so it will give a very small value. Otherwise, the resultant force will be equal to electric force minus the weight will be resultant force. But we neglect the weight of the electron. That's why we say the resultant force is equal to the electric force. As the mass is negligible, so weight will be very small. But we may have an object like maybe a spherical or a large object with a charge, spherical large charge object, which may have a considerable weight. In that case, when we substitute a force here, we will not substitute the electric force, we'll substitute a resultant force which will be equal to the electric force minus the weight if it is moving against the gravity. But because an electron is a very small particle or a small mass, so we neglect that value. Is it clear? Any question? If you want me to repeat any part, just let me know so I'll repeat that. So such type of questions are also there in which you have to determine the vertical displacement. You will find a repetition. I'm solving like different samples, so you will have an idea like how the question might be. Like a capacitor question, then electric field strength question, and then we have the Coulomb's law question. An alpha particle approaches a gold nucleus. It reaches a distance of 4.5 into 10 power minus 4 meter from a gold nucleus. So we have to calculate. So there's a gold nucleus which contains 79 protons. Neutron does not contribute here to electrostatic repulsion or attraction. As overall neutral, neutron is a neutral particle, and there's an alpha particle which is having 2 proton and 2 neutron. So what is the total charge? Because the charge of a proton, you check the end of the like where the constants are given, but the charge is same as the electron, which is 1.6 exponent minus 9. So the total charge of a proton, the Q1, will be equal to 2 into 1.6 into 10 power minus 19. Why not 4? Because neutrons are neutral, they don't have charge, that's why we don't consider. And the charge on the proton, that is 79 into 10 power 79 multiplied by 1.6 into 10 power minus 19. So we have the formula according to Coulomb's law that F is equal to K Q1 Q2 over R square, where R is the distance between them, which is given in this question, 4.5 into 10 power minus 14 meter. So we just substitute the value of the K is 1 upon 4 by epsilon, or you can also substitute 8.99 into 10 power 9, or 9 exponent 9 is also acceptable. And this will be, just substitute the values. So just substitute the values for the charge of proton, which is 2 into 1.6 exponent minus 90, and there is a gold nuclei which is having 79 protons, so 79 into 1.6 exponent minus 19 and divided by R square, which is 4.5 into minus 14, and then it will be 4 square. So when we substitute these values, we'll get about 17.9 Newton. So 17.9 Newton is the resultant force, not the result, like force experienced by each of them. 17.9 Newton, as their like charges repel, 17.9 here and 17.9 down. In question 10, some lights are designed to dim gradually after being switched off. This can be done by using a capacitor because capacitors will take time to discharge. As a result, what will happen, the component can operate for a period of a time depending on what is the discharge resistance. The circuit diagram shows how potential difference can be supplied across the resistor for a limited time. When the switch is at position A, the capacitor charge. In terms of movement of electron, explain what happened to capacitor as it becomes fully charged. So basic idea is that from a negative terminal, electrons will come out and they will stop here. And positive terminal of the battery will attract the electrons, so remove the electrons from the plate, so it will be positively charged. So what happened? That electron moved from so the idea is that because in the question they're asking that in terms of movement of electron, explain what happened to capacitor as it become fully charged. So because this is what happened initially, when it becomes fully charged, when the capacitor is fully charged, the flow of the electrons start to decrease. Like because like charges repel each other. So from a battery, electrons are not able to move because there is already lot of electrons or many like a net negative charge on one of the plate. So as the capacitor charge, the rate of the flow of electrons start to decrease. And when the capacitor is fully charged, the voltage across the capacitor is same as the voltage of the supply. Like if we have a supply 12 volt, this will also be 12 volt. So in terms of movement of electron, explain what happened to capacitor as it become fully charged. So when the capacitor become fully charged, the rate of electron flow decreases. And electron move from one plate to another through the external circuit, like moving out through the external circuit. Then the next part, calculate the energy stored in the charged capacitor. So if the capacitor is fully charged, the voltage across the capacitor will be 12 and we have the capacitance. So we have, because energy stored in the capacitor is given by formula half Q into V, or if we don't know the charge, so Q is equals to CV, so it will be CV square. The energy stored, because in place of Q we can write CV, so CV square will be there. So we have the capacitance and voltage, so half C is the capacitance 4700 micro, and the voltage is 12, that will be square. So when we multiply, it will be 0.34. 0.34 joules of energy will be stored in this capacitor. Then the switch is moved from position to position B and the capacitor discharged through a resistor. Describe what happened to the current through the resistor. When capacitor is charging or discharging, the current always decreases exponentially. So current will decrease over a time, and what is the variation? It will decrease exponentially. So even it is a charging or a discharging, the same thing happens for current. The current will decrease. 1 mark is for mentioning decrease and 1 mark is for exponential changes there when you are using a capacitor. The change is exponential, so you have to include that in your statement. For the circuit shown, the potential across the capacitor fall to 10% of the powers of the supplied potential after 25 seconds. Calculate the resistance. So we have the formula V is equals to V naught e raised to power minus T over RC. So 10% is what is there left. So what is V? V is 10%. So it will be 10% of V naught is equals to V naught e raised to power minus the time is equals to 25, and R we don't know, and the capacitance is 4700 micro. So when we simplify, V naught will cancel with V naught. It will be 10 divided by 100, that is 0.1, is equals to e raised to power minus 25 over R into 4700 into 10 to the power minus 6. We'll take ln both sides. So ln 0.1 is equals to minus 25 divided by R into 4700 into 10 to the power minus 6. When we simplify to get the value for R, that will be 2300 ohms, because R is there multiplied and ln 0.1 will go there in division. So when we simplify, it will give us 2300 ohms of the resistance. In question 11, we have to calculate the strength of electric field at a distance 5 centimeter from a surface of a positively charged. The diameter of the sphere is 12. Like this is a sphere which is positively charged. The charge on the sphere is 34 nanocoulomb, and the diameter of this sphere is equals to 12. So which is equals to 12 into 10 to the power minus 2 meter. So we want to calculate electric field strength at a distance 5 centimeter from surface. So we want to determine 5 centimeter from the surface of a positively charged sphere, and diameter of the sphere is given. So we'll use a formula. E is equals to kq over r square. So the formula E is equals to k q over r square, where k is 8.99 into 10 to the power 9. Q is the charge on the sphere, that is 34 nanocoulomb, and divided by the distance. So how we work out the distance? This is 5 centimeter, which will be equal to 0.05. And this distance, because we always take a distance from center. Now, when we work out, we always take a distance from the center. So this total is 12 exponent minus 2, or it means it will be 0.12. So if this is 0.12 meter, radius will be 0.06, half of it. So it's from center, this is 0.06 and this is 0.05. So when we sum, the distance from the center will be equal to 0.11 meter, because when we substitute this R is actually like the distance from the center. So that will be 0.11. So 0.11 and then R square. So when we substitute, it will be about 25,000 Newton per coulomb, or 25,300 Newton per coulomb. Is it clear, this question about the strength of electric field? So we always take a distance from the center of this sphere. Not that, because R is not the distance between the from the surface to the point where we want to determine strength. It is a distance from the center.